Welcome to the course of Principles of Vibration Control, and in the last class I have told you that how to design a classical control system with the help of various types of control block diagrams, but there are cases where you may not get a single input single output control. Let us say that we are considering a system which is like a lumped mass parameter system, something like this type of a system where there are more than one degrees of freedom. So, let us try to draw a system which has at least 2 degrees of freedom in it. So, we have this type of a system here which has a mass, first mass which is m1, and then we have a second mass which is m2, and the stiffness is K, and this is subjected to some kind of a force Ft. Let us say this damping is coefficient is C, and let us say that this is x1, the displacement of mass m1, and here it is x2, x1 as a function of t, xt as a function of t. So, this is not a single degree of freedom system anymore, this is a 2 degree of freedom system, and hence we cannot apply the same way in which we have done it for the last case of the classical control system. So, first of all let us try to find out that what is the governing equation of such a system. So, if I try to draw the free body diagram of the system, then we have this mass m2, the force working on it is F t, just put it as F t, and then you have the response as x2 t, which means the inertia force will be in the opposite direction, which is m2 x2 double dot, and also you have a spring here K, and that spring is having a relative displacement between x2 and x1, which is x2 minus x1. That is the first free body diagram. Then we will be having the second free body diagram for the mass m1. Now, in this case there is no direct force, but the spring is working. So, it is K times, it is just the reverse direction x1 minus x2, and then there is a damper that is resisting the motion. So, that is C x1 dot, and also of course, we have the inertia force which is in the reverse direction of the displacement x1 t. So, it is m1 x1 double dot. So, since this is what is our free body diagram, that means I can write down the equations of the system. In the first case it is m1 x1 double dot, and then we have this, of course, this is k x2 minus x1 in the reverse direction. So, k x2 minus x1, and hence if we want to put it all in the same directions, I can do it in 2 steps. C x1 dot equals to k x2 minus x1. In other words, and we can write it as m1 x1 double dot to the form which we know more, C x1 dot plus k x2 x1 minus x2. That means we keep it as a homogeneous form. And the second one, let us try to write it, that will be m2 x2 double dot and plus, there is no damping here, k x2 minus x1, and that equals to f t. So, this is my first equation and this is my second equation. Okay. So, I can erase all other things now, because these are what my governing equations are. So, I want to only keep my governing equations for the system with me. Once we understand the systems, we erase everything else to focus on the governing equation itself. So, these are the governing equations of this particular system, which is my first step in order to build the state space model of the system. So, as you can see that this governing equation consists of two second order ordinary differential equation. In order to decompose it into the form of a state space form, we have to convert each one of these second order ODE to two first order ODE system. How do we do it? Well, to do that, let us assume now that a new set of vectors which elements which we will call them to be the steady state elements of the system. So, we can try to find that out. That means, it will be x 1 dot as one state. So, let us call this as x 1 steady state, and then x 1 itself as another state. So, let us call that also as is the second state of the system. In order to just conform to the usual model, we may also do the other manner. That means, we can first put the x 1, then we can put the x 1 dot, and we call that as x 2 steady state. Then we can put the x 2 as the x 3 steady state, and we can put x 2 dot, and we can write it as x 4 steady state. So, what have we done here? We have simply considered for each one of these degrees of freedom, we have considered two states, okay? One for the position. So, this is the position, and another for the velocity. Now, we have to keep in our mind here that state space representation is not a unique representation, in the sense you could have considered any other linear combinations of these systems, or you could have considered velocity and acceleration as the two states, or position and acceleration, etc., etc. But in this case, the most common one is to go for position and velocity. That is what we have done for the 2 degrees of freedom of the system. Now, keeping this point in mind, let us try to rewrite this equation in a manner that it will become easier for us to convert it into 2 state space form. So, it will be m 1 x 1 double dot plus c x 1 dot plus k x 1 minus k x 2 equals to 0 as the first equation, and second equation will be m 2 x 2 double dot plus, we can write it as k x 2 minus k x 1 equals to f t. So, if we keep these points in our mind, let us try to see that how this representation is going to help us in terms of the state space representation of the system. First of all, by looking at this itself, we are going to get two identities straightforward. So, the first identity is telling us that x 1 s dot is actually x 2 s, because x 1 s dot means x 1 dot. So, I can write x 1 s dot equals to x 2 s. That is the first thing that I can get from here, and then I can also write similarly here that x 3 s dot equals to x 4 s. So, these two identities we can derive from these relationships that we have created. Now, let us look into this equation. In this equation, now we have x1 double dot. So, that means it is x2s dot. So, that means I can write this equation. So, let us write this equation now as m1 x2 s dot plus c x2 s plus k x1 s minus k x3 s equals to 0. That is what is my first equation, rewriting it, and the second equation also we can attempt to rewrite the same manner, that it will be m2 x3 s dot plus k x3 s now minus k x1 s equals to ft. So, we have these two equations also represented in terms of these new variables for us, and then I can try to write them down. So, my next equation, which is this equation, let us try to keep x2 s dot in one side. So, that means this equation, if we work one more stage on this particular equation, how will it look like? If I keep x2 s dot in one side, it would look like x2 s dot equals to, let us directly go to the other side now, equals to minus k over m1 x1 s and then minus c over m1 x2 s and then plus k over m1 x3 s. That is what will be this equation. And the last equation, let us look at it the same manner. We can write here as x2 s dot, and in this case we should have had written x4 s dot, because it is x3 s double dot. Okay. So, you can x4 s dot. So, that means the last equation will be for us x4 s dot equals to, let us put first the x1 term minus k over m2 x1 s, and then there is no term related to x2, then there will be minus. So, this minus k over x1, since we are going to the other side, it will become plus. So, minus k over m2, it is this one now, minus k over m2 x3 s plus ft divided by m2, because m2 we are dividing everywhere. So, plus k over m2 x1 s and minus k over m2 x3 s plus ft over m2. So, that is how we are going to get all the four equations, based on which now we can develop the state space representation of the system. So, let us try to erase everything else and focus on these four equations in a slightly more organized form. So, what we can do is that to do that, we slightly shift the position, we keep here x2 s, okay, so plus 1 times x2 s, that is what is one equation, and we keep here the last equation plus 1 times x4 s, and we shift this further away. So, we keep this as plus ft over m2. This will help us in terms of visualizing the system, and we slightly shift this also, minus k by m2 x3, which is here minus k by m2 x3 s, and here it is x4 s. Okay. So, we are nearly through with this arrangement. All we now need to do is that to write this system in a vectorial representation form like this. So, this is the complete matrix equation we will get. Left hand side we have x 1 dots, all x 1 dots together, and we now put them all into a single matrix. So, we bring these things together, we bring these things, we are building up the matrix now. We are going to write down these vectors here. So, let us try to shift this plus f t by m 2 further away, plus f t over m 2. We will talk about it, but let us just shift everything now for the time being. So, we have first one as x 1 s, and then for x 1 s first entry is 0, second entry is there x 2 s corresponding to x 2 s, then x 3 s and then x 4 s. So, we have 0, then we have plus 1, and then we have 0, we have 0. That is what is our first equation, right. So, you can write it as 0, 1, 0, 0, x 1 s, x 2 s, x 3 s, x 4 s for this case. Then we have the second one, x 1 s, we are already taking care of it, x 2 s we are already taking care of it, x 3 s we are already taking care of it. There is no relationship with x 4, so that is 0. Then we have the next one, this is 0, this is 0, this is 0, and this is plus 1, this is plus 1, and then we have the last one in which this is plus k by m 2, and then we have 0, nothing there, then we have minus k by m 2, and then we have 0. Actually, now that we have all the things there, so we can even erase the plus part because it is understood now. So, we have this is what is the first part of it. We have to still work on this guy. So, let us try to put this as an additional thing, where we will put it in such a manner that we have it in terms of something like a 0 and 1, keeping in mind that this is not affecting here. So, it is 0 here, the force is not affecting the second one, it is 0 there, the force is affecting here. So, it is unity here, and the force is not affecting here. So, it is 0 here, and this is a constant term. Now, in terms of the state space representation, this whole representation has a very formal way of writing. This part we will then call as x dot, where x dot will have all these variables. This one is known as A matrix A, then that plus x plus b. So, this is the A part, this is what is our A, and this is what is our x, this is what is our b, and this is what is the control input using which we are going to control the vibration. So, x dot equals to ax plus bu, and we are going to erase even this now, as in front of us we have a very formal state space representation of the system. So, we have seen that starting from the equilibrium governing equation, how you can gradually get the state space representation of the system, which we can write here as x dot equals to ax plus bu. Now, depending on what we are going to sense the output, we can also develop a similar equation for the output, in which there is no dot term there, but simply y as y equals to cx. That means some of these positions and velocities with some of the sensor gains we are going to observe. So, this is what is a kind of a representation of a state space model of a system. In this model, x is generally an n by 1 vector. So, x is n by 1, U is the actuation force which is generally less than n, it is m by 1. So, that means this is n by m is the structure of B. In our last case m was 1. So, that is why it was just a single vector, and A is n by n. Now, this one once again depends on how many outputs. Suppose if it is R, then it is R by n. So, this is how we generally define the sizes of the vectors. So, this is what is my state space model. The next thing is that how do I solve this state space model? We can talk a little bit about that. So, that will take the following form, that you have x dot equals to x plus bu, and what you can do is that you can take all the x variables in one side. So, you have x dot minus ax equals to bu. Now, let us multiply both the sides by e raised to the power minus at. So, it is e raised to the power minus at x dot minus ax equals to e raised to the power minus at times bu. Now, once we do that, we know that we can write this part as d dt of the product of e raised to the power minus at times x. So, this is known to us, and this equals to e raised to the power minus at times bu. Now, in order to get the solution, if I integrate this from 0 to t, integrate this from 0 to t, then we are going to see that we have this first part as e raised to the power minus at, the differentiation and integration will cancel. For the first part minus x 0, and that equals to integration from 0 to t e to the power minus a, let us give, because these two are same. So, let us give it a different variable, just e raised to the power minus a tau b u tau d tau. So, now we can actually write down the solution of the system as e raised to the power minus at x equals to x 0 plus integration 0 to t e raised to the power minus e tau b u tau d tau. And so, that would mean that I can actually find out x t as e to the power a t x 0. So, pre-multiplying again both the sides by e to the power a t, we can do that, plus integration of 0 to t e raised to the power a. Now, this will go inside t minus tau b u tau d tau. So, that is what is the solution of this particular state space equation. You can simply use this method in order to reach the solution, and if we denote e to the power a t as phi t, which is also known as a state transition matrix. Please keep in mind, A being a matrix, e to the power a t is a matrix. So, state transition matrix, then our x t can be written more formally as phi t x 0 plus integration 0 to t phi t minus tau b u tau d tau. Now, if you look at it, that there is a philosophical kind of a statement that we can make actually in this system, that the beauty of a state space system is that if you know what are the x zeros, which is the initial states of the system, then and if the phi t is available to you, which is a state transition matrix, which is nothing but e raised to the power a t, then you should be able to find out the states for any time t in future. In fact, that was the Newtonian model of a system of the entire universe, even that knowing the initial condition, you can find out what will be the condition at any point of time t. So, just you need two knowledges, of course, x 0 and phi t, and if it is a system in which you have some force part, then you have to add this forcing part in it. If there is no force part, then only x t will be phi t x 0. You initially displace it and then you see how the whole system is moving. So, you can start to visualize that this x 0 is actually, in this particular case, it is a 4-dimensional system, right. So, you have a 4-dimensional system that you have here x 1, x 2, x 3 and x 4. This 4-dimensional system is giving me the state space of the system, and in this particular case, in this 4-dimensional system, I am finding out how the entire states are evolving. Now, you can have a generalized case where you can have many more states like this and up to say something like x n. So, you can have n-dimensional system in which you can solve the same problem with the help of the state space formulation of the system. The other important point that we want to make here is that unlike the natural frequencies, the counterpart here is actually the A itself. So, you can in fact once again find it in this manner that x dot equals to a x plus b u. So, if you use the Laplace transformation, then it will be S x equals to a x plus b, let us call it as x bar and b u bar. So, that means S identity minus a times x bar equals to b u bar. Now, for a homogeneous case where I am not I am not applying any force to the system, then this is 0. So, that means I will be having S I minus a times x bar S equals to a null matrix. So, for the non-trivial solution of this determinant of S I minus a must be equal to 0, and this is going to give me. So, this is what is my new characteristic equation. Earlier we have talked about the characteristic equation, and this is the new characteristic equation of the system. So, you are going to get, let us say, if A is of n by n size. So, you are going to get a polynomial of S, which is S n plus some constant, let us call it alpha 1 S n minus 1 plus dot plus alpha 0 equals to 0. So, instead of getting actually a second order characteristic equation, now you have a nth order polynomial of characteristic equation which you can get from this determinant. So, you will be getting actually not 2 roots, but S 1 to S n number of roots you are going to get from this system. These roots are also known as eigenvalues of the system. So, instead of having just a pair of eigenvalues, in the case of a state space system, you are going to get n number of eigenvalues, and of course, if they are of a complex type, then they must be complex conjugate, because otherwise my equation here is having all real terms. So, you will not get it. So, that is why you will get it either as S1 to Sn real or S1 to Sn as a combination of real and pairs of of just complex conjugate roots. So, that will be a complete representation of the state space system. With this representation, in the next talk we are going to talk about that how we can use a full state feedback control for another kind of multiple input multiple output system. Thank you.